Okay, so above the core, or the outer core, I should say, we have what is the mantle in the chemical composition, or we have what the layers that are subdivided here in the physical properties composition, right? A lot of people that think that the mantle is liquid and that it's from the mantle that the magma comes and that it is made up of the same materials as those in the mantle. So even though some of the magma does come from the mantle, it doesn't mean that the whole mantle is made up of the same materials that magma is made out of. As most of you probably know, magma, which once it reaches the surface through a, say, for example, a volcanic eruption, becomes lava, is liquid. However, most of the mantle is actually solid. So although magma does come from deep within the earth, it is much more liquid and much lighter in density than the mantle is, and even than the crust is, which is partly why it actually rises towards the surface due to its lack of density or low density. So the mantle itself is the thickest layer in terms of composition, and it is around 1,850 miles thick. It is composed mostly of iron and magnesium-rich silicate rocks, meaning rocks that are made out of mostly silicon and oxygen, and either magnesium or iron as the bonding elements with those rocks, with those elements, with silicon and oxygen. The average density of the mantle is 4.5 grams per centimeter cubed, so less than half the density of the core, which is partly why it rests on top of the core rather than below it, right? But the density is still more than 4 times denser than that of water, so it gives you a comparison there. The mantle is split into 3 main layers when we consider the physical properties. So in this image here to the right, you can see that it's split into the mesosphere as the lowest layer, and by far the largest and deepest one. The mesosphere itself is pretty solid. The asthenosphere follows it. So if you guys remember from the previous slide, let me show you that real fast. When you take this box, mesosphere here is at the bottom, asthenosphere is relatively narrow, and then following the asthenosphere is the lithosphere, right? So let's go back to that, where we were. But mesosphere is by far the thickest, and it is pretty solid. The asthenosphere, which is again following it, it's a liquid section of the mantle, or maybe not liquid, but definitely more mushy. And it lies in the middle of the other 2 layers. And then finally you have the lithosphere, which is rigid and solid overall as well. And the uppermost layer is the lithosphere itself, which also, looking at the lithosphere and comparing it to the chemical composition, the lithosphere is going to be made up of the crust and the uppermost layer of the mantle. Okay, I know that might seem a little bit confusing, but when you compare the thicknesses of, again, the lithosphere, asthenosphere, mesosphere, and then the crust and mantle, you will see what I mean by that. So we'll talk about the asthenosphere and the lithosphere in more detail later within the lecture as well. So don't fret if that is confusing for now. So once you move towards the surface from the mantle to the crust, you move into a much thinner outer rocky layer. The crust is the thinnest and least dense of all of the chemical classification layers. It's only 2.8 grams per centimeter cubed on average, and it is also subdivided into 2 main parts. However, this subdivision is not a subdivision that comes with depth, but rather depending on spatial location. So it doesn't mean that, I will divide the first 2 kilometers of the crust and then the latter 3, but rather here it will be different than over here, okay? So one subdivision is the oceanic crust, which is thinner. So the oceanic crust is only 6 to 7 kilometers in thickness, which is a little under, like 4 to 5 miles or so. And it is slightly denser than the other subdivision, which is the continental crust. So the continental crust is somewhere between 35 to 70 kilometers thick, depending on where you are. Actually, less than 35 in certain areas. The average is 35, but it goes up to 70 kilometers thick in other areas. So the oceanic crust contains more iron and magnesium than the continental crust, which is why it's denser. And it's relatively young in comparison to the continental crust, as we will see later. It is younger than, most of the oceanic crust is younger than 200 million years, whether the continental crust can be as old as 4 billion years in certain cases. So the continental crust again is thicker and it's less dense than the oceanic crust, and it contains mostly sodium, calcium, potassium, or aluminum elements, which will also bond with the silicon and the oxygen, as opposed to the oceanic crust, which had mostly iron and magnesium bonding with the silicon and oxygen. And so that combination of elements, sodium, calcium, potassium, aluminum, since they are lighter elements, it will make overall the crust, the continental crust, less dense. And it will allow it to rest above the oceanic crust if they ever meet. We'll cover some of those dynamics later on in the chapter, so no worries. The continental crust is much thicker. As I said before, it averages 35 kilometers, which is 5 times as thick as the average of the continental crust. So very, very thick. And in certain places, typically below what are mountain belts, it is up to 70 kilometers in thickness. So the continental crust is much older on average, with the oldest parts being again up to 4 billion years old. And the reason for this, again, will hopefully become clear as we go through the rest of lecture. And it's also much thicker. In the previous slide, I described the mantle and the crust, but I just wanted to also talk about the Moho subdivision, which you are seeing right here. So the Moho, or the Mohorovičić discontinuity, is a sort of line that separates the denser mantle from the more buoyant crust. It was found through the use of seismic wave reflectance and the speed of travel from those seismic waves. The crust, being more buoyant or less dense, means it sort of floats on top of the mantle. So the Moho is about 5 to 10 kilometers below the surface, depending on where you are within oceanic crust, and it lies between 20 to 90 kilometers in thickness or in depth below the surface, depending on where you might be within continental crust. Okay, here we will look at 2 layers from the physical subdivision that are especially important for the plate tectonics mechanics. So those being the asthenosphere and the lithosphere. The asthenosphere lies towards the top part of the mantle, as we saw in the previous slides, but it's still within the middle. So remember that the mantle went way further here. This is the mesosphere, the bottommost layer of the mantle. Then you have the asthenosphere right here. So it is still in the middle, which means that it's sandwiched between the mesosphere and the lithosphere. It is very hot, and it actually does flow in a more fluid manner. Its texture is kind of, or it resembles sort of like silly putty. So it's not liquid, but it flows in a plastic manner, allowing for more easy movement, right? It is between 60 and 120 miles below the surface, depending on where you are, meaning whether it's oceanic or continental, and whether it's where within the continental or oceanic areas. And it goes up until 450 miles below the surface, which it makes it about 3 to 400 miles thick, basically. Above the asthenosphere sits the lithosphere, which is the topmost layer of the physical properties, right? Subdivision. The lithosphere itself is going to be colder and hence more rigid than the asthenosphere. It is the outermost layer of the Earth in terms, again, of the physical properties, and it is made up of 2 chemical composition layers. The uppermost is the uppermost part of the mantle makes up the lower part of the lithosphere, and then the whole crust makes the upper part of that lithosphere. It doesn't matter whether that type of crust is oceanic or continental. And so we also refer to lithospheric parts as being oceanic lithosphere or continental lithosphere, just so that's clear in your mind for now. So on average, the lithosphere is 60 miles thick, which makes it much thinner where you have oceanic crust and much thicker where you have continental crust. The behavior between these two layers, the lithosphere and the asthenosphere, is super important to understand in this chapter, because the plates, or the tectonic plates as they're called, are made up from the lithosphere, and they sit atop the asthenosphere. They are also therefore referred to again as lithospheric plates because they are made up of lithosphere. And a pretty good analogy to understand how they act, how these plates act, sitting atop that more malleable asthenosphere, is by thinking, for example, of a bunch of bathroom or kitchen tiles that are placed on top of wet mud or wet cement. So if you were to step on those tiles, they do move relative to one another, right? Because they're sitting on wet mud and wet cement. And if you get the cement wetter and wetter, those tiles might even actually flow on their own without you having to step on them, for example. As I was saying a couple of slides ago, we know that the continental and that the oceanic crusts differ in density and in thickness as well, the former being much thicker and less dense, and the latter being thinner and denser. The oceanic crust contains elements such as iron and magnesium, as I had said before, which are denser and hence more compact, which also partly explains why that layer is thinner. And the continental crust contains elements like sodium, calcium, potassium, which all tend to be lighter in density and less compact, filling up more space for their weight in comparison, which partly explains again why it's thicker. So both types of crusts contain plenty of silicon and oxygen. That's an important thing to have in mind. Silicon and oxygen make up most of the bonds that are made with any of the other elements I mentioned. So when you have oceanic and continental crust contact one another, pushing towards one another, the oceanic crust will actually sink below the continental crust because it's already denser, sitting deeper below the continental crust as they meet. It is because of this that oceanic crust is much younger than continental crust, because every time that oceanic crust meets continental crust, the oceanic crust sinks below the continental crust and eventually turns into part of the mantle with the help of heat and pressure, basically. But the continental crust stays above, it stays atop that oceanic crust that sunk below. So it will never get destroyed. So it continues getting older and older, whether the oceanic crust gets destroyed before it accumulates much age. So that is why we have parts of the continental crust that are nearly the same age of the Earth, only a little bit younger, because the first 500 million years or so of the Earth's formation, there was still no clear subdivision of the Earth's internal structure, or at least definitely not of the crust. So, as an example, there are places, for example, in Montana and in Idaho, where you can find rocks that are 2.5 to 3 billion years old, even at the surface. And you could never find such old rocks in the oceanic crust, not even close. So that's just showing you how much different these two types of crust may be and what we can find about them. This will all also make more sense as we go through the slides later on in the lecture.